Alright, go ahead and get started. So welcome everybody back to EE290C. Today we're going to talk a bit about sort of basic transmitters and receivers. So we spent some time kind of talking about just system level components and what the backplanes and PCBs and etc. really look like. Today we'll actually start diving into some of the circuits. Before we sort of dive into the technical stuff, just sort of a few administrative notes. So number one is that I'll be out this Thursday, and just because of scheduling, I didn't manage to find a way to sort of tape ahead that lecture, so instead I'll sort of tape it back, so to speak. So we'll have, instead of lecture on Thursday, we'll actually hold that on Monday. I'm going to try and do that from 1:30 to 3 o'clock just here in this room. So again, if you can show up, please do. Hopefully most of you can actually make it. If not, again, that's fine. So definitely don't show up here on Thursday because no one will be here. But on Monday, please do, and then we'll resume sort of normal schedule from there on out. Also, because I'll be out, I won't have any office hours that day. But of course, as usual, I'm available over email, and certainly, feel free to get in touch if anybody has any questions or anything like that. I imagine nobody will have questions just yet since I haven't actually posted the homework. But the plan is to do that later this evening, and so certainly if you have questions and things, feel free to get in touch, and we'll get those handled. So, any other sort of logistical kind of stuff, or actually questions on material from last time, or? Okay, maybe just to do one quick poll. So how many of you guys have already sort of figured out who you're going to work with for the project? Oh, not that many. Okay, well, so as I said, definitely get going on that because the project will be a very large component of the overall class. So you'll want to make sure you sort of get that figured out relatively far in advance so that, you're kind of ready and waiting to go as soon as I, hand out that first handout or whatever it is. Okay, so unless there's any other questions, we can actually go ahead and sort of dive back into the real material. So, as you've maybe seen as a theme a couple of times for now, the way I wanted to actually just sort of start things out in terms of how you'd really build the basic transmitters and receivers is actually to go back and look at, what's wrong with that really quote-unquote silly picture that I drew in the first place of making a link just be something like a flip-flop, an inverter, the wire, which of course we saw the wire was actually something much more complicated. That was the whole backplane with connectors and stubs and etc. And then the receiver maybe just having another inverter and a flip-flop and, just why don't we build our links that way? So, let's actually throw that out to you guys. So what's sort of wrong with building a link this way? What are some of the issues you guys can think of? And I mean specifically, well, it's actually not just the circuits, but, what are some of the issues that you guys can think of? Okay, well, so you said it's single-ended. Now, we're actually going to talk some more about that. That in and of itself is actually not a bad thing. So, and we'll talk again some more about this later, but single-ended means that in theory I only have one wire instead of two. So actually I could even argue that there's an advantage, but what's the problems with it being single-ended?
Just the noise immunity.
Okay, when you say noise immunity, what do you mean?
So if you have any coupling from nearby signals, you won't be able to reject any common mode.
Okay, so that's right. So what you mean by that is basically there's no common mode rejection, right? That's certainly true, just because it's single-ended. And of course, let's actually even look at the circuit itself. So what's bad about this particular circuit as, for example, being a receiver? Why don't you just throw inverters on there and say, that's my receiver? How many of you guys used an inverter for your 240 project? Well, that was in the transmitter, not in the receiver. I remember that. Shiva?
Yeah, noise. Maybe I could do a noise.
Okay, what about noise? And by the way, to be technically precise, I think most of you guys are talking about interference so far, and not thermal noise. But so do you mean interference or do you mean noise?
I mean, in general, you need to have a good noise margin for the inverter at the receiver.
Okay, when you say noise margin, what exactly do you mean?
I mean, if there's any coupling, it may give you a wrong logic level. So,
okay, coupling from where to where, for example?
I mean, any other digital circuitry nearby, like ground switching, supply switching, something.
Okay, so you're sort of saying something about supply switching or ground switching. So actually, that's a very good subject here. So what do we think is going to be happening? Well, actually, let's even take one step back. So remember, the whole goal of what we're trying to do here is decide when the transmitter sent a 1 and when it sent a 0, right? So sort of implicitly, how is that inverter deciding what's a 1 and what's a 0? What's setting that?
Threshold.
Okay, there was the threshold. You said something about, the threshold of, now, is this a threshold of the devices or?
Yeah, so
the transmitter and receiver is kind of far apart, so the PMOS-NMOS ratio might have some difference.
Okay, so you said that, you know, this is chip number 1, this is chip number 2, and of course those chips are, you know, whatever, I don't know, 36 inches apart or whatever. In fact, although actually that probably doesn't matter that much because it really matters, you know, when they were fabricated or in fact where in the wafer they were. So you just said those things are very different, and so who knows that, you know, my PMOS to NMOS ratio in that inverter was anything that was good in terms of setting the threshold to be something close to what this, you know, inverter over here is actually sending out. There's a lot of truth to that. I'll claim there's actually even something more, let's say, fundamentally busted with this. So what else is, let's say, fundamentally busted?
So the grounds on the 2 are not the same.
Ah, there we go. So the grounds on the 2, even if I had this, you know, big, huge PCB, and I actually had a big, you know, ground plane connecting things together, sorry, they're 36 inches apart, right? Ain't no way in heck that the ground on this particular chip is the same as the ground on this particular chip. Okay, now, turns out there's even something bigger that's going to exacerbate that particular issue. And so, by the way, just to highlight that, I'm going to draw sort of a big inductor between the grounds over there. Anything else related to the power supplies? Or actually, maybe even before that, how is it that this inverter is deciding what thing is a 0 and what thing is a 1? Like, how does it make that quote-unquote decision? What was like the first thing you learned about inverters back in 141? What was like that really annoying thing that I said is just annoying to calculate, so I probably won't do it that often, but then, you know, I just showed you a couple of them and said, you know, it was important for this to look a certain way, to be digital.
Are you worried about how to set the how to bias the inverter, like self-bias?
Yeah, okay, so by the way, what do you mean by biasing? Or let me...
Noise margin, right?
What's
I mean,
that?
Noise margin, the butterfly curve, and all that.
Okay, noise margin, but so you said, so everything you're saying is sort of related to it, but maybe I'm sure you guys sort of will get this as soon as I say it. There's a V out versus V in curve over here, right? Okay, and you know, ideally if I had an inverter, it should look something like that, right? There's some magic point at which before that it would say it's a low, and above that it would say it's a high, right? What sets that magic point?
PMOS-NMOS ratio.
Okay, there's a PMOS-NMOS ratio in there. Anything else?
Supply voltage? The supply?
Yeah, the supply voltage, right? So in other words, the only thing that's telling you what's a 1 and what's a 0 is the supply voltage. Well, guess what? We just said the grounds are completely different on the other side. Okay? So now, even worse than that, what's particularly bad about this kind of transmitter here from the standpoint of actually getting the inverter on the other side to receive what you think is a 1 and what you think is a 0?
You'll have a supply drop, and there'll be IR drop through it.
Okay, so you will have some IR drop or whatever. Let's assume that I do a good job, I know how to build the backplane, and I actually even make that magically pretty low. There's actually even a more nasty issue.
Swing of the signal itself.
Say that again?
The swing of the signal itself.
Swing of the signal itself. Well, okay, I mean, so by the way, if I really did this, actually, I think the swing is pretty darn big, because it's just the power supply.
The digital stuff are modulating the supply.
Ah, okay, so you said something about the digital stuff modulating supply. That's actually absolutely correct. Turns out, even if I didn't have that, I claim that just from this picture that I've drawn here, there's something pretty nasty that's happening.
The two supply might be different.
Yeah, okay, but why?
I mean, like you intentionally make the supply different because the transmitter you want different swing, because that basically says swing and receive.
Okay, right, so you actually even took it a step further. You said, well, maybe I'll intentionally skew the supplies or something like that. That's certainly true. Let's even make those the same. I still claim this is probably busted.
I mean, even if the absolute value of the supply is the same, you still have that inductance between the ground, so the supply minus the difference, potential difference across the cell is going to change.
Yeah, so that's absolutely right. So this ground and that ground certainly are not at all the same thing.
Effectively like having different supplies. No?
Okay, that's true, but I'm actually trying to get at, you know, internally what's happening. And Charles, maybe you have an idea.
You have that clock right there, right? So you actually might have some kind of clock feed through into the inverter, and then you see some spikes. That will actually change the decision of that inverter.
Okay, so that's true, although, by the way, that's like, you know, maybe second or third order. I want like the 0 or first order.
You don't have the termination, right?
Okay, that's right. I don't have any termination. That's right.
That's going to pass. If
Okay, so you said that's really bad. That's true, and actually you'll see in a homework exactly how annoying that is. There are actually certainly a lot of issues related to not being terminated. By the way, this particular thing may not be correctly terminated neither on the transmitter nor on the receiver, right? So it is certainly true there's going to be a lot of signal integrity issues because of that. But there's going to be one more, like, really important one that, you know, just about everybody complains about.
If the wire has sufficient loss, both transmitted 1 and 0 will be below the threshold.
Okay, so, well, that's actually an interesting one. So it depends on, let's say, what the data pattern here was. Because if the data pattern was sort of balanced, then maybe I could magically balance it around the threshold on the other side. But you're right that if I had a long string of zeros and I had some low-pass filtering, I may not make it back over. Yeah?
Because you can't regulate the supply on both sides?
Ah, well, so what do you mean by regulate the supply on both
You need a
sides?
supply regulator, right?
Okay, but I think I still have a supply regulator, so let's even do this. And I'll do it over here somewhere just so I've got some space, okay? You've got this chip, right? And it's inside of a package. And let's say you even put a regulator, right? Let's say that's another chip that's kind of sitting over here, and I don't know, this is, what do you guys think? 10 millimeters away, okay? So what's like a good model for my supply network? What does that look like? Yeah, I see somebody making the right symbol. How would I model my supply?
Inductance.
Yeah, so I'm going to have, let's say, there's somehow magically an ideal voltage source inside of that regulator there. Well, guess what? There's some inductance actually to get on to my darn chip. Right? And then inside of my chip, okay, I've got this inverter thing. Right? Well, what happens when I change the state of that inverter? So what happens when I change it from, for example, outputting a 0 to outputting a 1? What happens to the current through the supply?
You're sourcing and sinking current.
Yeah, so if I looked at, let's say, the current flowing through that inverter there, anytime I have a transition, it's going to look something like, maybe like that, okay? Well, so what happens when you have a spike of current that you dump through an inductor? What does the inductor like to do?
LDI over.
Yeah, it just says, no way, sorry, if you want that much current change, then I'm going to cause a huge change in the voltage, right? So let's actually even draw the full circuit over here.
But don't you have bypass caps for that?
Ah, okay, great. You said, don't you have bypass caps for that? Well, guess what? You're absolutely right, I have bypass caps. So let me even put bypass caps. But now, does me having a bypass cap right here help me at all, given the fact that actually some current has to flow out through that transmission line? And then come back, guess what? Through that ground loop? Not so much, right? Because the bypass cap just makes sure that this relative to that is fixed. It says absolutely nothing about this ground over here being the same as that ground over there. Right? In other words, if you kind of think of this like a cartoon, every time you have a transition, one of those chips is totally free to just bounce around like this. Right? So if like the on-chip supply is the distance between my fingers on the two sides, all the bypass cap does is make sure the distance between my fingers doesn't change. It says absolutely nothing about me doing this, right? Which if you think about this nice big inductor here, I'm totally free to move that common mode, well, I've called it common mode, I should really be careful. I'm totally free to move the ground on one chip completely separately from the ground on the other chip, okay? So we'll actually talk about this some more. It turns out one of the biggest issues with sort of single-ended drivers is anytime you send current out through the chip, then your return path always also has to go through that outside thing. Okay, and if those chips are far apart, guess what? No way in heck of guaranteeing that there's even remotely the same idea of what ground actually is. Okay? Now, don't get me wrong, it's not that this is completely busted. You can eventually make things work, but if you try to make this go at really high frequencies, pretty tricky. Okay, pretty tough to really make it work the right way. Okay, so what I was kind of getting at, and maybe those questions can be related to it, go ahead.
Because when you say you have an inductance on the return path, you're assuming you have a single wire. But what about you have a transmission line and the return path is part of the transmission line?
Ah, but still basically there's an inductance associated with that, right? So even for you to have that transmission line, like you said, I had to have a ground plane and that wire, right?
Right.
So if I think about the current that's flowing through that transmission line, it's always going to be flowing back through that ground plane.
Yeah, right, but then it's more distributed, per se.
It's still distributed, but nonetheless, what's the impedance between the chip that's 36 inches over here and the chip that's, sorry, between two chips that are 36 inches apart. Nothing to say that, those two grounds are actually very tightly tied to each other, right? Because all it takes is for me to pull some current around over here that goes through some other ground return paths that have nothing to do with this signal, and I'm moving around all over the place, right? Yeah?
So why can't you just run the ground plane also? I mean,
you do indeed run the ground plane, but the question is just how good of a job can you do really getting your signal to be strongly coupled to your local ground, both on your chip and on the chip that you're talking to, right?
So what I'm saying is instead of running the wire like that, I mean, you run the ground also like as he said.
By the way, I think what you're saying is why don't you just run a differential signal?
Yeah, exactly.
Right, which indeed is a lot of times what you're going to try and do. Okay, so we're actually going to talk about this a lot more. Turns out one of the, let's say, the big debates on differential versus single-ended is when somebody says you can do single-ended with just one wire, can you really actually make it work with just one wire? Okay, because basically because of these return path issues, you can imagine if I really just had, let's say, one ground for every 5, 10, 15, 20 of these IOs, guess what? The bounce that you would get on one chip relative to the other one would be so large there's no way in heck the thing will actually work. Like you're talking multiple volts now, by the way. So I'll give you some more of the terms related to that, but that is indeed actually a very big problem. Okay? So there was actually something else that I think maybe Linkai or somebody brought up, which is, okay, right now my swing is just sort of set directly by the power supply. Right? So if I've got, let's say, a 1 or 1.2 volt supply, and I want to actually run some swing onto this 50 ohm line here, then at least temporarily I'm going to be burning something like 20 milliamps. Okay? So actually it turns out if you were really to do sort of a high-speed signaling kind of thing with something that looked exactly like this, probably going to end up burning you quite a bit of power. Okay? And we'll talk some more about why exactly that is a little bit later. Okay? So this was kind of maybe to give you guys sort of, let's say, a global overview of what some of the issues we're going to be talking about are, and I think we've maybe hit just about everyone, except for maybe one of them. So there's one more thing that turns out to be a little bit bad, in fact, perhaps a lot bad, about not having things very well controlled like this, which is that basically if I look at this transmitter here, there's really nothing controlling sort of how fast I transition between 1 and 0, right? And so you remember I said that this inductor here doesn't like you to allow you to change the current very quickly. So of course, the faster you try and change the current, the more voltage drop you're going to induce, right? Turns out that similarly, even if you looked out on this, sort of on the channel over here, that backplane with the connectors and etc., if you put really, really sharp edges in, then every single tiny little discontinuity that may be physically small, you'll actually be able to see, right? Because a sharp edge sort of implies that it has a very very small wavelength, right? So it turns out that actually from a crosstalk standpoint, a lot of times you really want to be able to control how fast you change states just to make sure that you don't end up exciting a bunch of extra junk all over the system that ends up killing you somewhere else that, of course, could be very complex to figure out exactly what was causing that crosstalk in the first place. Okay? So I actually won't, and I'll just put it down here just simply because I won't talk about it later, but edge rate control is also sort of a pretty big issue that's kind of not at all addressed by this particular design here. Okay? And again, by edge rate control, I just really mean controlling how quickly you actually transition between the states in order to control how much essentially noise you, or rather interference you induce both on yourself and on the rest of the system. Okay? So what I'm hoping to do sort of through the rest of today is give you an idea of sort of what are some of the basic circuits that you'd really be dealing with in terms of both the transmitters, and actually I'll focus mostly on the transmitters here, and then I'll talk a little bit at the end about the receivers. And I've sort of done it that way because my assumption is that, again, most of you guys took 240, and so you spent a little bit of time kind of hacking on the receiver. And so I think the transmitter is probably more interesting for you to learn some more about and kind of see what the issues there are. But basically, it'll kind of give you an idea of just, what are the different types of, let's say, signaling that you can use, and what are the trade-offs between them. We already talked a little bit about single-ended versus differential. We'll talk also about sort of the circuit design of the transmitter, in particular, sort of how you'd control the output impedance, what are the different types of drivers you might work with, what are sort of the power consumption versus swing trade-offs, and things like that. Okay? So unless there's any more questions, let's actually sort of dive into this first, single-ended signaling thing. So basically, the real issue that you get into when you're talking about single-ended signaling before I just drew the thing as being sort of an inverter in terms of the receiver, but I could indeed actually try and build some sort of differential amplifier as my receiver. Okay? The problem really that you get into there is that if you're actually talking about single-ended, what you're kind of implying is that whatever you're using to set the reference for that differential amplifier is somehow shared, right? It's somehow being used in multiple different links. Okay? So the problem is that as soon as you share it, well, again, of course, there's a multiple different return paths, and so obviously you're going to be affected by what all of these different things that you're working on, or all of the different links that are sharing that reference, are going to affect what exactly that reference actually looks like. Okay, so basically it turns out there's no really good way of getting a shared reference that really does actually match perfectly. Okay, so you almost always end up with some sort of mismatch and therefore some residual interference that you have to deal with if you try and do that. Okay? The other, which again we spent a lot of time talking about, which is just sort of highlighted here in a cartoon, which is that given that I have these ground return paths here that have large inductance in them, anytime I sort of pull some current through that thing, I'm going to cause this bounce over here, which again is going to cause the entire chip to move around relative to chips on the other side, okay, or really relative to the board ground. So this particular thing is sort of a big enough issue that people came up with its own name. So usually they call it SSO, which I believe is simultaneous switching outputs noise. So the idea here is, imagine you had like a big bus of signals. Let's say you had, I don't know, 30 or 40 of these inverters, each one driving 20 or 30 milliamps instantaneously. You can imagine if they all happen to transition the same way at the same time, big, huge glitch of current, big, huge movement of the entire chip relative to the entire ground. Okay? So usually it turns out that in order to do this, or in order to basically handle this, you actually end up having to put a pretty substantial number of ground or power supply connections just to make sure that your sort of impedance to the rest of the world is sufficiently low. Okay? The other thing that, of course, we talked about is if I do something like this, then I really don't have any crosstalk immunity, right? Because there's no such thing as a common mode for me to just dump all my garbage into, right? It's single-ended, so quote-unquote everything is common mode, right? Everything will show up directly on your signal, okay? So now, of course, the question is, and this is why I sort of, let's say, teased Stephen a little bit when he said it's single-ended and therefore it's bad. You could think that, okay, well, if single-ended has all these bad characteristics, then, why did I even mention it? Why did I even bring it up as being a possibility? So what do you guys think? Why is single-ended actually still used quite often? And, sort of the picture here is supposed to give you a hint. Yeah?
Board area is limited, so...
Right, bingo. So, I've got a certain size board with a certain size number of chips, or a certain number of chips I want to pack onto that thing. And if I need, a certain, let's say, a terabit per second of throughput, well, if I can get twice as many single-ended links as I can differential links, hey, great. Then maybe I can actually get more net throughput per unit area, right? Or to say it another way, maybe I can make that bus smaller than it would have been if I had to use those differential links. Okay, so indeed, and that's kind of what this picture is trying to show. Right, there's just these wires kind of running all over the place. And in fact, I think if you look even up into the latest and greatest sort of high-speed DDR memories, or high-speed DRAMs for sort of graphics processors, most of those are still actually single-ended. Okay, and they actually have very, very wide buses, something like 1,000-something pins just to sort of get communication between the DRAM and that graphics processor. Okay, so what this is kind of saying is that, yeah, single-ended is nasty, but basically it is still actually a very valid, let's say, option in terms of trying to get things to work. Okay? So there's sort of this classic debate among, let's say, I/O designers, in particular, of course, among people that have patents on differential signaling versus patents on single-ended signaling about why X should be better than Y, right? So the classic argument from, for example, the guys who want to do single-ended stuff is they say, well, okay, fine, yeah, differential, that's great, but you have to be more than twice as fast as the single-ended signaling in order for it to be worth it, right? Because the simplistic argument there is that you have 2 wires for every sort of link that you form, whereas the single-ended one has only 1 wire for every link that you form, okay? So, again, that's a rather simplistic argument. The reality is obviously a lot more complicated. And in particular, as we mentioned, the sort of simultaneous switching output noise, or this SSO noise, really does tend to cause you to actually have to use physically more pins, even for that single-ended signal. So typically you can only get away with maybe about 4 or 5 pins, even single-ended, before you'd actually have to put another ground there just to get a sufficiently low sort of return path impedance. Okay? So that's where you sort of start getting into, let's say, these more philosophical arguments about, okay, well, is it really a factor of 2, or is it a factor of, 1.5, or, what's the real number, and, how much harder is it to get the single-ended thing versus the differential, right? So I wouldn't claim that I necessarily know the answer there. But, if you force me to give an answer, and of course, since we're taking a class, I'll try and give you some sort of answer that I think makes sense. The short, quote-unquote, answer there is just that it's a heck of a lot easier to get a differential link to work. Okay, so if you do things sort of reasonably well with a differential link, you can be pretty confident that you can sort of stick it into most systems and it will actually work the way you expect it to. With single-ended, not really the case. Okay, with single-ended, you really have to think very, very carefully about every single little piece there, because if there's any sort of noise source that or interference source that you forgot about, it very easily could, be completely wiping out your signal. Okay? And obviously, the higher sort of frequencies you go, the more of these types of issues you have to worry about. Okay? So simply for that reason, I will mostly focus on sort of differential signaling in this class. But that's not to say that single-ended isn't, an option. It's a viable option. Just, from an engineering standpoint, it takes a lot more manpower, a lot more brain power, a lot more, chips that basically are dead the first time they come back in order to actually get it to work the way you want it to. Okay? Does this kind of make sense to people, or? Okay. Question?
So right now they're looking at area and throughput. What about the power comparison?
You could make that argument as well. Now, power is, let's say, a more interesting question in the sense of, as we'll see a little bit later, where you end up spending power in the link really strongly depends upon what's the environment you're operating in and kind of, how good you are at, let's say, reducing some of the overheads associated with just the signal processing you have to do. But to zero order, and we'll talk about it a little bit more, you could, in theory, actually spend less power with a differential link for the same swing as you can with a single-ended link. And I'll explain why I say that in maybe a couple more slides here. Okay? But that's purely from the signaling standpoint. So it's probably actually the case that, if I really could get it right, single-ended may turn out to be more efficient, just because I sort of have less stuff inside of there. The problem is only, how hard do I have to work to actually get it to work the right way? And okay, so maybe by the time I've done that, I've probably maybe even actually spent, the same or more power as I would have in the differential signal. So it's a good question. I wouldn't claim I necessarily know the answer, but I think the simple answer is that, most people, particularly in, let's say, the fairly long distance types of links, really just say, look, I want to make this thing work. I'll just go differential and I'll pay the penalty in terms, or the quote-unquote penalty in terms of the throughput per unit area. Yeah?
I actually have a question in terms of how do you actually define you can actually make the single-ended work? Because you just talk about it's kind of like sensitive to crosstalk, right? And let's say you have like 64 link and you're going to kind of like see things kind of messed up already.
Mm-hmm.
So you're going to hurt your BER, right? So in terms of BER performance, how does single-ended compare with?
Well, so there's no fundamental reason why single-ended can't get low burr, right? So remember, that's why I'm going to try and use the distinction between noise and interference.
Uh-huh.
What typically limits a single-ended link is not noise, it's interference. Right? So the question there about getting it to work is really a question of finding what's actually causing the interference on your signal and figuring out how to get rid of it. Right? So either adding more grounds, adding some shields somewhere, increasing the swing so you get more margin, doing a better job of coupling the reference to your actual signal, and so on and so forth. Okay? So again, it's not to say that there's fundamentally it can't be done. It's only a question of tracking down where each one of these 10, 20, 30, 40, 50 millivolt kind of interference things are actually coming from, and making sure you can get rid of them. That's really what it's all about. Does that make sense? Or? So actually, maybe to put it into context, this is a lot like the wireless problem. Okay, so in a wireless where I have an antenna and just anything can come into that antenna, well, kind of same idea with a single-ended link, right? Just about anything can make its way in there, and so you have to be a lot more careful in terms of how you sort of set things up to actually make it work. And actually, the disadvantage in links is that usually you don't have some, very nice bandpass filter sitting right at the front of your quote-unquote antenna to at least knock out stuff that really has nothing to do with it, right? Okay, good. So now that we've sort of talked a bit about, let's say the single-ended versus differential, and as I said, most of the time, at least in this class, I'm going to sort of assume that we're going to be talking about differential signaling, simply because I want us to be productive and get things to actually work. The other, let's say, bifurcation that you'll hear very often is what's called voltage mode signaling versus what's called current mode signaling. Okay, and so I've only shown sort of the equivalent of a single-ended driver here, but at least the conceptual idea is that oftentimes what people are sort of trying to refer or thinking of in the back of their head is a voltage mode signaling looks something like this, where I sort of have a switch between one of the two supplies, and that's sort of how I decide what the output is. Whereas a current mode signal is something where I sort of dump some current out into the line in one direction or the other, and that's how I sort of decide whether the signal is a 1 or a 0. Okay? Now, the first thing I should mention here is that, of course, any transmission line, if I put a voltage onto it, guess what? It's going to have a current also, right? It's just sort of electromagnetic wave. There's always some impedance associated with that line that gives you a relationship between the voltage and the current. Okay? So it kind of begs the question as to, well, what do you really mean by voltage mode versus current mode? Right? Because, okay, I mean, maybe in terms of the circuits that inside of here, I kind of understand what the difference is. But, in this context of actually doing some signaling on a transmission line, not quite as obvious. Okay, well, it turns out that to make life even more, let's say, annoying, the terminology of voltage mode versus current mode is actually fairly heavily overloaded, meaning it can mean a few different things in different contexts. Okay? So really what it sort of is supposed to mean is voltage mode just means that your sort of impedance is low compared to everything else you care about, right? Current mode means that your impedance is high compared to everything else you care about. Well, so unfortunately, again, as I said, what you care about is different in different contexts. Okay, so sometimes it means, as I've sort of said, whether or not the output impedance of the driver is high compared to the line. Sometimes they actually use this to mean how you've set the output impedance of the driver, and you'll see what I mean by that in 1 second. And sometimes all they really mean is what actually sets the output swing. Okay, meaning sort of the magnitude of the output signal that you're putting onto the line. Okay. So just to make this, let's say, a little bit more specific, what I wanted to do is just sort of draw a few different examples of drivers that you might actually see. And then I'll try and sort of, quote-unquote, classify them by whether they would be current mode or voltage mode. But I'll try and point out what people really mean when they say that. Okay? So the first kind of driver is, of course, the thing that I've been harping on as being really bad for a while. But, actually turns out if we do things sort of right, so to speak, maybe it's not so bad. Is basically just, again, this good old inverter. And in this case, I'm going to say that that inverter is just running off of some power supply, what I'm going to call VTT, meaning it could be separate from the supply of the rest of the chip. Okay? There's another kind of driver, which is also actually fairly common, which is still basically an inverter, just that now what I'm going to do is stick an explicit resistor in series with it. Okay? And then here I'm going to make that resistance, roughly speaking, equal to the termination resistance. Okay? That's yet another kind of driver which is actually also fairly common. Okay? The next thing I'm going to do is basically just have something where I'm only going to have, in this case, the pull-down transistor. Okay? But I'm going to load that with some termination resistor. Okay? And so let's call this driver C. So in this particular one, by the way, I'm usually going to sort of arrange the gate voltage here. And again, I'm going to run this, by the way, off of VTT. I'm going to try and arrange the gate voltage there so that that transistor actually stays in saturation. Okay? In other words, it doesn't go sort of into triode and look more like a resistor. Okay? The final one, which is really basically the same as C, but is just really sort of the differential version thereof, is, of course, just something that looks like a differential pair, but has sort of a bias current inside of it. Okay, so these are still VTT. Okay, this is just the termination resistance on both sides, and of course, I'm going to feed it with differential data at the input. Okay? So let's just walk through and sort of, well, let's maybe take a guess as to what we think for A, B, C, and D. Oh, and I forgot to label D. Here we go. For what each one of those different drivers, when you say voltage mode or current mode, well, let's first guess, what we think is a voltage mode and what we think is a current mode. And then let's also sort of be more specific as to what we really mean by that. Okay, so for driver A here, you guys think that's voltage mode or current mode? Yeah, it's voltage mode, right? That's usually a pretty obvious voltage mode driver. Okay? Now, what do you really mean by voltage mode here? So I claim there's actually sort of two things that's kind of implied by quote-unquote voltage mode in this particular driver here.
The FETs are in triode. I mean, they're
Okay.
sized very large so that the resistance is pretty small.
Okay, so you've said basically the FETs are in triode. So I'm going to twist that in a slightly different way. What you're basically saying is that the output impedance of the driver is set by the devices. Right? That's kind of what you're saying. Okay? It could indeed be low, by the way. But actually, since I didn't show you any sizing or anything like that, you don't actually know if it's really low. Because I could have made them small, and then it could actually be high compared to the transmission line. So it's really just set by the devices. Right? Okay. What's the other sort of thing that's implied by this particular driver? Just in terms of the list of, 3 different things that I mentioned in the previous slide. There we go. The swing is set by the voltage, right? The swing here is set by VTT, right? Okay. So now, for B, voltage, current, what do you guys think?
Current?
Oh, I don't know. So what do you guys think? So by the way, I think I know what may have caused you to say current, but usually people think of this as being a voltage mode driver, and I'll explain why that is in 1 second. Okay? So usually people think of that as being a voltage mode driver. Okay, so again, in this context, what do I probably mean by that being a voltage mode driver? Like, what are the sort of 2 criteria that I'm applying here? Or what are the 2 things that are being set by each other?
Output impedance.
Say that again?
Output impedance.
Okay, so now the output impedance here is being set by what?
Device and RT.
Say that again?
Device and RT.
Okay, so you're right, it is actually both the device and the termination resistance. But usually if I do this, I probably intended to set it by the termination resistance. Okay? Probably. That's obviously, it doesn't have to be that way, but that's probably what the intent was. So most of the drivers that you see that look like this, that's actually what they intended to do. Okay, so that means that the devices themselves, those would have to have very low impedance. And so that's why those look more like, let's say, a voltage mode driver. So Eric, like I said, I understand where you got to your current mode because, I could have actually done it in a different way, but usually that's what they actually mean. Okay, now how about the other parameter? What else is going on with this one? Which is probably the more direct way to say that it's a quote-unquote voltage mode driver.
Swing is set by supply.
Yeah, the swing is set by the supply, right? Okay, so now, hopefully it should be obvious, but how about C and in fact, of course, also D? What do you guys, is that voltage mode or current mode?
Current.
Yeah, it should be current mode, right? Because like I said, you'll usually arrange this thing so that the transistor itself stays in saturation. Okay, so this indeed is usually a current mode driver. But okay, so now, again, in that context, what do I mean in terms of the things we've been talking about? So what's supposed to be setting the output impedance here? Yeah, RT is supposed to be setting the output impedance. Okay? So in this particular context, we sort of mean that it's current mode in the sense that the transistor output impedance is high. And so whatever I explicitly put there is really what's controlling the impedance. Okay? Okay, now how about on the, let's say, the other so-called vector or axis there? What else do I mean?
Bias current.
Yeah, so the swing is set by the bias current. Okay? Okay, so now I'm just going to put this bias current sort of in parentheses because it's not quite as immediately obvious what I mean by bias current in that particular case, but you can imagine I can sort of arrange the gate voltage so that it's a mirror or something and it sort of looks like a bias current, Just, I don't know, wave your hands furiously and hopefully you'll see it. Okay? So what I really mean, of course, by both of these, or really to have sort of, both of these things happen, that does say the devices have to stay in saturation. Okay? Because that's kind of how I get them to be high output impedance, or rather how I get them to be current sources, and sort of have both of these properties that I've tried to make happen actually happen. Okay? So let's actually sort of take another look at this. So here I'm just sort of showing you, like, if I was to split between singlet and a differential, hopefully that's pretty clear. But if I also was to split, let's say, between quote-unquote low impedance and quote-unquote high impedance, okay? And again, low impedance here is kind of implying voltage mode, and high impedance is kind of implying current mode, okay? Now, in these particular designs that I've shown you here, I actually am not, let's say, doing everything that I may need to be doing, which is, in particular, I'm actually not terminating on both sides, okay? So notice, for example, in this design here, I may have added these explicit, resistors in my voltage mode drivers there. So I've maybe got 50 ohms right here, but on this side I've left it open circuit, okay? Similarly in this current mode driver, actually over here, I've said, okay, I'm not going to put a resistor on the transmit side, I'm only going to have it on the receive side. So my transmitter actually looks like an open circuit driver, and on the receive, that's where I've sort of, I just put some resistors there to grab that current and convert it into a voltage, okay? So, two maybe questions here. So, first question is, why might I want to build something that looks like this? Or alternatively like this, meaning where I only really terminated one side. Why might I want to do that? Maybe somebody other than Shiva. If not, we'll just come back to you. What's good about not terminating both sides? Yeah?
You get more swing because you don't have parallel signal.
Yeah, bingo, right? So if I think about it, if I really put a resistor here and a resistor there, right? Guess what? Half of my current is going to go into those resistors, which means I'm going to get basically half of the signal swing for the same amount of current I spent, right? So hey, if I can really get rid of those things, great. I'd rather just get twice as much signal for the same power, right? So you should notice here that, of course, if I have a current mode driver, on the receive side, you want to put a low impedance to suck all that current out. Of course, on the other hand, if I have a voltage mode driver, you want the receive side to have a high impedance so that you get all of the voltage that you applied, right? Okay, so the good thing about doing this was, as we just said, if I didn't terminate, on one side, then actually I get twice as much swing as I would if I do terminate on both sides. What's the bad news? Got to be somebody else besides those two in the corner. Yeah, reflections, right? So here I've got an open circuit on the receiver, so things will hit the receiver and bounce back, right? And okay, maybe that does mean that I actually get twice as much voltage, but it also means I probably cause twice as much crosstalk and have twice as much chance of creating a resonance somewhere that I don't like, right? Similarly, of course, over here on the transmitter, if I have an open circuit transmitter, if anything ever comes back and hits the transmitter, guess what? It'll just turn right back around and go back to the receiver, right? So there's sort of this, let's say, signal integrity trade-offer that you get into, right? So that's actually kind of what I was really sort of planning to drive into here, was just to say, as we already said, if I really compared something that is terminated on both sides, and kind of the equivalent model for that is something that looks like this. Right, so I have sort of my source over here that has a 50 ohm source impedance, and similarly a load that has a 50 ohm load impedance. If I again, of course, compare that to something where, for example, let's say I only had the source impedance, but I left the load as an open circuit, indeed, at least at DC, you would indeed get twice as much swing in this case for the same power. Okay, so sounds kind of attractive. Turns out, again, actually most of the time people don't really use this. Not because it's impossible to get it to work, but only because you have to worry about a lot more stuff now, right? You have to worry a lot more about, well, okay, if it's not terminated, then basically what's really going to happen when I put this into a backplane? How likely is it that I'm actually going to sort of hit this thing and then reflect back and then come back again and so on and so forth? Okay? So basically people like to actually put terminations on both sides simply to try and sort of keep the signal integrity as high as they can, just to be more robust. Okay? Just to really make sure that you can predict what's going on and really actually ensure that it's going to work the way you want it to. Okay? And again, sort of the intuitive reason for that is that if you terminate on both sides, you're kind of containing the energy, right? You kind of know what's going to happen when you launch something. It's just going to get absorbed and it'll stay there, right? Whereas if I don't terminate, then it's very easy for me to just launch some voltage thing that bounces off, comes back, bounces somewhere else, couples into some other receiver, bounces off of something over there, comes back, and so on and so forth, right? So it's really just kind of an issue of managing complexity and trying to be robust, okay? So indeed, for most links that you're likely to encounter, they probably will actually terminate both on the receiver and on the transmitter, even though that implies that you actually pay a fairly substantial penalty from a, let's say, swing versus power standpoint. Okay, and that's really just, you want to be robust. There's kind of no other great way of ensuring that that's the case. Okay? Does this make sense to people, or? Okay, so turns out there's a lot of steps that people will take, again, just to sort of try and ensure that things are robust as they can be. So just as an example, even if you looked at even if you looked at just taking your chip, for example, you can imagine I could take my chip and actually, package the whole thing, and then have my output driver, but not actually put the termination resistor on the chip. I could actually put the termination resistors out on the board, right? If you actually compared that against really putting the termination resistors on the chip, turns out you can even actually see a difference between those two from a signal integrity standpoint, okay? Because the reason for that is that basically, if you actually put this resistor on the chip, then now the inductance that you get either from your bond wire or your C4 bump or whatever it is that you have to get basically from the chip out through the package and into the PCB, and the capacitance that you have sort of sitting on your pad, this looks a lot more like the transmission line, right, if I put the termination here. Whereas if I put the termination out over here on the package, I kind of have this stub. Right, I have this little piece of transmission line looking kind of thing that's going into the chip and just is open circuited, right? So if you look at sort of the difference between the blue and the red waveform here, the blue is what would have happened if I really put the termination on the chip, whereas this red is just having that little stub from getting basically from the package into the chip. Okay, and so you can see it actually caused this little ripple kind of thing from the reflections happening inside of that little stub. Okay? So generally speaking, especially if you're really sort of pushing on the limits of performance, you tend to want to put the termination resistor on the chip. Okay? Now, let's say the bad news about that. Why is it that that you might have wanted to put the term resistor outside in the first place? What do you guys think?
Not be accurate?
Yeah, so turns out it's a lot easier to just buy relatively accurate external resistors than it is to actually get intrinsically very accurate resistors on the chip itself. Okay? So the bad news about, bringing the termination resistor onto the chip is that now you actually have to do something to make sure it really is the value you want it to be. Okay? So the simplest thing that indeed is actually pretty common is if you want to do a termination resistor, you just say, okay, screw it. I have poly resistors on my, process perhaps, which of course just looks something like this, where these are just the contacts. And I may just have a slab of unsilicated poly. Oops. Okay, so indeed, that's kind of a very straightforward way of just trying to create the termination resistor in terms of either the series element or that parallel element that we talked about for voltage mode versus current mode. Okay? Yeah?
So, if you're going to have an on-chip resistor, so what do you do for measurement purposes?
What do you mean?
If you want to measure a chip or something, your VNA or whatever is external is going to provide a 50 ohm impedance.
Oh, but so the question was, if I have an on-chip termination resistor, then what do you do about measurement? Actually, having the on-chip termination resistor a lot of times is better because the instrument is indeed expecting a 50 ohm term, right? And so if I have the chip that already has the 50 ohm term in it, I can just hook into that chip, whereas if I don't have the 50 ohm term, then I may get some standing waves, or I may get some large reflections, or I may have to add an explicit resistor externally, right?
Doesn't that actually change the termination which the chip sees? It becomes like 25 ohms, right?
Oh, yeah, so of course. So you're absolutely right that, if I looked at, for example, this equivalent model here, right, the impedance at that point is indeed 25 ohms, right? So when you design your circuit, you should expect to see 25 ohms there and not 50, right? Which, by the way, just about anything that's terminated as the driver and terminated at the receiver, if both of those are 50, you're going to get 25 ohms at that node, right? That's just life. Which, by the way, is another way of saying I have half the swing for the same current, right? Other questions on that? Or? Okay, so again, just coming back, as we said, if we're going to put the termination resistor on the chip itself, then one of the most straightforward ways you can think of is just, okay, fine, I'll do a poly resistor, right? Well, that works kind of reasonably okay, but the bad news is that, if I don't really do anything, and in most processes I'm going to get, I'm probably going to have at least plus minus 20% variation in that poly resistor in terms of absolute value, right? Not only that, that's only really just at one temperature, right? If I was to change the temperature, that poly resistance value also will move even beyond that plus minus 20% or so. Okay, now, in some links, that's probably okay. It's probably good enough, right? You just say, okay, I'll just measure my link with kind of the worst case termination resistors and make sure things actually work there, right? But sometimes when you're really kind of pushing the edge of what's feasible, you really can't tolerate that plus minus 20%. You really need to actually bring that down even tighter to really make sure that you've got that last, few millivolts of margin that you needed to make the thing actually work. Okay? So, oh, yeah.
So in our cost-sensitive PCB, what kind of variation do we expect on the...
Okay. So obviously it depends upon the resistors that you can get. But, sub 5% tolerance or so is pretty straightforward to get, even in a relatively low-cost part.
I mean the transmission line.
Oh, in the transmission line itself. Okay, that's a great question. Depends on the exact PCB. But it's generally quite a bit better than this, especially if you're not sort of pushing the limits of what the process can actually do. So largely that's just sort of driven by the thickness variations, and those are reasonably good. So I don't remember the exact numbers, but I think those are in the order of plus minus 5% or so. And in fact, if you go and you specify to the PCB manufacturer, hey, this is a controlled impedance line, please be careful with it, you can probably do even better than that. So, there's certainly some variation there, don't get me wrong, but it's not usually too bad. Usually there's more variation in sort of loss characteristics and things like that with temperature and with humidity and things of that nature. But the impedance itself usually is reasonably well controlled. Okay, so kind of the long story short of the poly resistor, of course, is it's really simple, right, which is nice. It's pretty linear, which is good, especially if you're going to be dealing with really big transmit or receive signals, right? It turns out it's also very ESD robust because, hey, it's just a resistor, right? And in fact, sometimes you even want resistors to just limit the amount of current that you'd flow in an ESD event. And the other thing which turns out to actually be very critical in some applications is that I really don't have very many parasitics from this resistor, especially if I have sort of a nice high resistivity unsilicated poly device, okay? But again, if I really have to do a better job in the control, well, we have to work a little bit harder to actually make that happen. Okay, so we'll come back to that a little bit later on. There's actually one other thing which I've sort of hinted at a little bit here, which is to say that this thing has low parasitics, meaning it has low parasitic capacitance. Turns out that can also be quite important. Yeah.
I mean, for the on-chip resistor, right, it's not just the untrained poly. You can do some kind of long metal line, which have more.
Okay. So you could indeed do a long metal line. If you do a really long metal line, the problem I think you'll run into is that this particular statement I'm making here will no longer be true. Because if the metal has to be, 110 millimeters long or whatever it is, and I snake it around 20 times to get, a few kilo ohms, probably going to be pretty big and have a lot of capacitance.
What we're talking about is 50 ohm, right?
But so remember, even if it's 50 ohms, I can't do a 0.1 micron wide metal wire and actually get 20 milliamps of current through that thing, or even 10, or even 5, or even 2, right? I actually have to make it pretty wide, which of course means then it has to be pretty long. So you're right, there may be cases where you can get away with it, but generally speaking, you're still actually better off with something like an untrimmed poly, simply because for parasitics, you want it to be kind of physically as small as you can make it. Does that make sense? Or other questions on this? Or okay, so now, why are parasitics important? Well, hopefully that is somewhat obvious, but just in case you haven't thought about it before, turns out that especially if you looked at some of these shorter type of channel applications, turns out the biggest issue you have in terms of the channel is not the wires between the chips. It's actually just how much junk do you have at the pad, specifically how much capacitance do you have at the pad, and what is the impedance that that capacitor sees. Okay? Now, by the way, this is actually a particularly important issue if you were to ever try and build a bus. Right? And by a bus, I just mean something that, for example, would be one transmitter talking to multiple receivers, because every single one of those receivers would add more parasitic capacitance onto that bus. Right? So what this picture here is kind of showing you is you add, let's say, more and more chips onto that bus. Basically, the pole that you pick up just from the 25 ohms that we talked about before, times the sort of effective capacitance that you have here, I just keep stacking up more and more of those poles and basically filtering the actual signal that I get more and more heavily. Okay? So just to give you an example of sort of, why this is actually a reasonably big deal, and again, this is especially true in these relatively short distance kinds of applications, it's pretty common for your ESD protection to have somewhere in the ballpark of 500 femtofarads of parasitic capacitance. Okay? Don't take this as an exact number, but this is definitely the right ballpark. Okay? Your driver or receiver, okay, here actually I maybe fudged this a little bit just to make the numbers easier, but that could actually, in fact, in older technologies, that could very easily be on the order of 500 femtofarads or so, just from all of the different transistors and legs and ESD protection and various things that you'd put there. Okay? And in fact, by the time you're done doing all that, you have to route all these things together. Just the wires to connect them, which again have to be pretty wide because they're carrying a lot of current. Those could also be about another 500 femtofarads or so of parasitic capacitance. Okay? So in total, you could pretty easily have about 1.5 picofarads or so of cap just sitting out at that pad. Okay, and by the way, when I say wire, that actually also includes the pad itself. Okay? And I should mention CI, that's kind of like the input capacitance. That's kind of like this total lumped thing. This RI, as I've kind of noted over here, is you may even have some resistance in series with it as well. But long story short, if I just take this 1.5 picofarads of capacitance, and I calculate what's the sort of filter that I get off of that with my 25 ohms, that's already down somewhere in the sort of 4 gigahertz range or so. Okay? Now, by the way, you actually have that capacitance on both sides of the link. So if I was to include that, now I'm down at about 2 gigahertz or so. Right? So like I said, if you really want to be doing these relatively short distance kinds of things, even if the wires themselves are not lossy, I could be picking up basically loss or really low pass filtering just from my own pad capacitance. Okay? And so for those of you guys who remember, equalizers from 240, if not, don't worry, I'll talk about it more later. Sometimes people will build equalizers just to equalize the pad effect. Okay? And not for anything even remotely related to actually getting out of the chip. Okay? So, as I said, this is, particularly bad if you end up doing buses, or for some reason you add some series, a big series resistance somewhere. Again, obviously that low pass filter just gets even worse, right? So the bottom line is you really have to be careful about, how complex of a thing you put at the pad. And in particular, as I mentioned over here, how much parasitic capacitance your termination resistor includes. Because if you're not careful, you can actually end up filtering your signals pretty badly just from your own circuits that you ended up building. Okay? Okay, so given that we said that there are actually these situations where just untrimmed poly just doesn't quite cut it, then there are a lot of people that spend time just looking at, what are various different active termination structures you can actually build. Okay? So let's just kind of quickly look at a couple of those. So the first one, and for now, by the way, I'm going to be assuming that everything is sort of terminated up at the supply, so I'm just going to draw sort of, let's say, the PMOS version of things, but you can imagine you can also do this with NMOSs as well. So simplest way, of course, to build something that's just a variable resistance, and I want it variable just so that I can actually control it to be 50 ohms, is just as an example, take a PMOS transistor and feed a variable gate control voltage to it. Okay? So let's say the good and the bad news about something like this. And I guess maybe I'll give you the only piece of good news. So the only piece of good news is it is tunable. What's the bad news? Say that again? Okay, so that's right. Even though it's tunable, you'll need to build a loop to tune it. unfortunately, that's pretty much fundamental. You know, if I have something that's tunable, then, you know, unless somehow magically it's both tunable and always lands exactly where I want it to be, in which case I don't know why it needs to be tunable. You know, that's kind of fundamental. But you're absolutely right. You have to build a loop that will actually tune it.
Linearity?
Oh, I heard, yeah, it's nonlinear, right? So, and in particular, it's nonlinear versus VDS. Okay? Now, depends on the application. This may or may not be a big deal. But particularly if you have pretty big swings that you're dealing with, that may start to get kind of nasty, right? Because remember, the whole point of doing this was because you wanted a pretty precise resistance. Well, if the thing is nonlinear, then what does that even mean that you made it quote-unquote precise at one particular bias point? Okay? Yeah?
Extra parasitics.
Yeah, exactly. It's also got extra parasitics. Right? Because basically for the same sort of unit resistance that I could have gotten from that poly resistor, I'm going to get a lot more cap from this structure. Yeah?
Probably pretty sensitive to ESD.
Ah, okay, so that's right. It is actually not the most ESD robust. Right? So I actually have to be pretty careful to make sure that this thing won't blow up, you know, instead of just, you know, something else, because, hey, this looks a heck of a lot like my active circuits. Right? So that's actually also absolutely correct. Okay, turns out the ESD, well, okay, I'll show you one structure that's maybe a little bit better from that standpoint, but ESD is a pretty tricky one. You basically just have to sort of make things work, and if they don't, you're pretty much hosed anyways. Okay, so that's not necessarily great. You know, it kind of works, but maybe it's not the best. Anything else you guys can come up with, which is maybe a little bit better, or maybe is a little bit, let's say, easier to deal with? I'll give you a hint. This is like the analog way of doing things. What's the other way of doing things?
Digitally trimmed resistor?
Yeah, just a digitally trimmed resistor, right? So, of course, that also is just something quite straightforward. You just take a bunch of these PMOSs, you segment it into different, you know, little legs here, and maybe I'll make it smaller so I leave myself room for the last version. Right, you have some digital codes on here, D2, and of course this just continues depending upon how many different legs you want. And basically you can, of course, do the digitally controlled version of this same thing. Okay, so turns out from that standpoint, it basically has pretty much all of the same advantages and all of the same disadvantages. The only maybe potential advantage here is just that, okay, the loop may be digital versus analog, and so maybe that's a little bit easier or a little bit more robust to build, or you have to worry about it a little bit less. But otherwise, it's basically kind of the same thing as what's happening here. Well, okay, I take that back. There's one minor, let's say, difference here, which is that in the digital version, I can really switch the gate all the way from VDD to ground, right? That means that I can really try and put this thing as far into the linear region as I possibly can. Whereas with something like this, there's going to be process corners where that VC will not really be down at ground, right? And so from a linearity standpoint, it will be more challenging to actually hit the linearity you want, okay? So there is that, you know, slight benefit there. So let's say from here to here, it's maybe slightly less nonlinear. Okay, but still does have pretty potentially large parasitics. Actually, even there, maybe it's slightly less than this version, but still pretty considerable. Okay, any last version that people can think of that maybe is kind of slightly better? In fact, in some cases, quite a bit better?
Resistor in parallel with it.
Yeah, okay, so what you basically said was, well, why don't I put a resistor sort of in parallel with that programmable thing? Okay, now what's actually good about that? Why does that even help? I'll see if anybody else gets it. If not, I'll come back to you.
Carries most of the current.
Okay, what's good about that? Steven?
Oh, I had a different response.
Okay, well, let's see if we can figure it out from that. If not, we'll just go over to Steven and we'll see. It is actually related to what you said, by the way, but let's see if Steven gets it.
My response is that now the tuning range of the PMOS active device is now smaller, so the
Bingo.
linearity is better.
Bingo, right. So if I really do that, and by the way you typically end up doing something like this looks sort of like this. So those other legs that you do the tuning on, you actually also put some series resistance in them. Okay, and then again, these are, of course, some digital codes over here. So that's really the reason why this turns out to be a little bit better. Because what I can basically do is I can put kind of a resistor there that isn't exactly the resistance I wanted. It turns out it has to be a little bit bigger. But now in terms of the tuning range, what I really just have to cover is sort of the variations that I expect, right, on sort of that nominal resistor. Because if I was to try and build that entire resistor out of something that's tunable, that also means it's probably going to vary a lot more, right? So here what I'm just sort of trying to do is decouple, okay, let me get something that, you know, is kind of close to a best guess, and then just only pay the extra parasitics for tuning around that sort of, let's say, nominal bias point, so to speak. Okay? So this also turns out to then be less nonlinear, simply because still most of your resistance now should be coming from sort of that nominal leg over there. It turns out also to have a little bit less parasitics for kind of the same reason. Okay? And I think that's basically, yeah, that's, you know, okay, maybe it actually has slightly more ESD robustness just because you have resistors in series with everything rather than gates directly on the output node. But, you know, that's not a huge effect. As I said before, you still need to worry about the ESD protection. Okay? Question? Or?
Yeah, so what's the benefit of having a resistor in series in each of those legs?
Ah, okay. So the first one is actually related to ESD protection, which is just that I don't have anything directly sitting on the output pad. That's not a huge deal. The other is just that, again, if these resistors are slightly more well controlled than the transistors, then in terms of sort of the dynamic range you need to cover in the variation, it's a slightly better dynamic range here. That's all. It also has a slightly, you know, it depends on exactly how it's sized. It does also sort of slightly isolate you from the parasitics of those caps. In other words, it creates a zero in the response that, you know, if that zero is sort of in a, let's say, nice enough point, then you'll actually be somewhat isolated from the additional cap there. Right? Obviously, it depends on how exactly you've sized the thing, but that's the sort of first order answer.
Yeah, so in this kind of a tuning scheme, like, it's not linear, right? So,
well, it's linear in conductance, which is obviously meaning that it's nonlinear in resistance. So when you do something like this, that's why I've sort of drawn it in the digital version. Because in the digital version, you know, sort of just, it says something about the step sizes that you're taking, but as long as your maximum step size is sufficiently small, you may not care all that much.
But then the individual resistances, some of them may be pretty large. That's what I mean.
Say that again?
I mean, some of the resistances may be pretty large.
Yeah, so there is certainly a trade-off here in terms of how you size these resistors, in terms of, let's say, the maximum step size you get versus the number of unit elements you really need to deal with. The good news is that, remember, we're only dealing with plus minus 20%, and I probably only need to knock that down to like plus minus 5% or so. So I'm not trying to build, you know, like a 0.1% precision resistor here. I'm just trying to really get this to within the range where it basically doesn't have an effect on my overall signal integrity anymore. But you're absolutely right. It's not that this is a slam dunk. It's got its own design issues. Okay, great. So unless there's sort of more questions on that, there's sort of one other quick thing that I would just want to mention in this context, which is actually related to a question that Stephen asked before, which is that if I really move to differential signaling, it turns out there's one kind of simple trick that I can play, which is we'll hopefully see today, and if not, we'll see next time, actually can get you a slightly, in fact, even perhaps fairly substantially improved efficiency from the standpoint of signaling power. Okay? So the trick that you can play here is, you know, so far I've mostly been showing these things as sort of being terminated in a single-ended way. Right? So I've always been sort of putting 50 ohms to the equivalent of ground. Right? Well, if you think about in differential signaling, instead of putting 50 ohms to ground, what I can basically actually do is put 100 ohms in between the two differential lines. Right? So this so-called RAC over here, I can actually make it, for example, 100 ohms. Okay? Now, you might think, well, okay, why does that really matter? Well, if you sort of think about it, the swing I get is always related to the current that I use times the impedance. Well, if I can actually deal with 100 ohms impedance instead of dealing with 50 ohms, hey, guess what? I'm going to get more swing for the same current. In other words, I can actually burn a little bit lower power. Okay, so this is kind of a nice trick to increase my overall system impedance that I'm dealing with. Okay? So as I said, we'll see this in more detail a little bit later on, but this is indeed actually a pretty useful potential trick. Okay? Now, it turns out when you do that, if you're only terminating in the differential mode like that, well, there is now a problem, right? I haven't actually terminated the common mode if I really do it exactly like this. Okay, and that's a problem because, of course, if I don't terminate the common mode, I'll get common mode reflections, and okay, fine, I'm putting all my junk in the common mode, but there's only a finite amount of common mode rejection you're actually going to get. Okay, so to actually get the common mode rejection, there is actually just one more small trick that you can play here, which is typically really the way you would do it. So does anybody happen to know how you can make this structure still actually give you a reasonable common mode termination? And I'll give you a slight hint. It'll only be at least over a certain range of frequencies. Yeah?
You split the 100 ohms into 50-50 and put a large resistance to common mode or directly connected to common mode.
Okay. Well, so you almost... So which one of them is it? So you said I can split that 100 ohms into two 50 ohm resistors. That's good. Now what do I do?
Hook up the midpoint to...
What do I hook it up to?
Whatever common mode you want.
Okay, so now, let's say I really do hook it up to a voltage source, which is V common mode. What impedance am I dealing with now?
50.
I'm dealing with 50 ohms, right? Not with 100. So how do I still deal with 100 ohms? Say that again? Okay, well, I can put a large resistance, but by the way, if you put a big resistor there, then, again, the bad news is that, you're basically open-circuited and sort of it doesn't really look like a common mode term anymore. But there's one more sort of trick you can kind of play, which, as I said, at least over a certain range of frequencies, gives you the termination.
The inductor?
Okay, I heard a few different options. I think I heard inductor. I think I heard the right answer, but I don't know if I heard it.
Capacitor?
Yeah, capacitor, right? So if I basically put a cap here to ground, then at the frequencies where the cap kicks in, now it actually looks like a good common mode termination, right? And so indeed, that is actually a pretty common technique that people will use. Obviously, at lower frequencies, it's not really common mode terminated, but hopefully, down in those frequencies, you don't care all that much because there shouldn't be a whole lot of reflections going on in any case. Okay, so indeed, that's typically sort of how you construct something like this. Okay?
What's the typical frequency corner you put over there?
Oh, so that varies pretty widely. It could be anywhere from, let's say, 10 up to a couple hundred megahertz or so.
For like 50 ohm, for like 10 megahertz, you need like a huge cap over there.
It is big. It is indeed big. But that's life. Not much you can do about that. By the way, there is, let's say, another sort of thing to keep in mind here, which is if I really terminate like this, then now my common mode is really set by the transmitter, right? Now, it turns out that can be inconvenient for a few different reasons. So why might that be inconvenient? What do you guys think? Yeah.
Now, the supply moving around my kicks into play.
Right, exactly. So now, because my common mode is directly set by the transmitter, if the transmitter is bouncing around relative to me, then that's sort of directly coupling into my common mode. Right now, okay, so maybe I hopefully have a high common mode rejection in the receiver, but indeed I'm sort of much more coupled than I used to be. Right? Any other, by the way, very practical reasons why that might be a little bit annoying?
You might want a low swing at the transmitter to reduce power.
Okay.
So which means your common mode will be pretty high. Right?
Okay, it could be.
Yeah,
it depends on how you actually do it, but yes.
Compatible with the receiver side.
Okay, so what you said was, if I have my transmitter over there, then let's say I want to have the swing relatively low, that may make the common mode very high. That common mode may be bad for this receiver. Okay, it turns out you can actually even have the flip problem as well, which is in fact, it's probably even more common, which is most of the things out there are shared ground, but separate supplies. So if I end up tuning the supply in one chip and not on the other one, I could very easily tune the supply in my transmit chip to fall out of the common mode range of my receiver, right? So in fact, sometimes people will do everything as sort of ground referenced simply to avoid dealing with that particular problem, okay? But what this basically says is if you really directly do it the way I've shown you here, it does tend to be a little bit annoying simply because, you may actually get that wide common mode coupling, or even just from a practicality standpoint, if you're dealing with a bunch of different transmitters and I didn't spec exactly what the common mode is, I may have to make the common mode range on my receiver quite wide. Okay? So, of course, in order to deal with that, oftentimes what people will do is just stick these AC coupling capacitors in here, so that at least at DC, the common mode is decoupled from the transmitter versus the receiver. And then, of course, what you can do is just add in some sort of large common mode resistors to actually control what the common mode going into the receiver is. This does turn out to be quite nice, by the way, because, just to think, in case you think I was crazy, if you actually look at sort of, all the different signaling standards out there, and you wanted to build one receiver that actually worked on all of those, you'd see that the common mode range is anywhere from about minus 0.5 volts up to about 1.5 volts, okay, which is obviously a real pain in the ass to build in a sub 90 nanometer technology, right? So indeed, decoupling things like this is pretty nice, but of course it places some requirements on the signal, or rather the data itself, because these AC coupling caps mean you lose things at DC. Right, so if you've ever heard the term baseline wander or DC drift, that's associated with these AC coupling capacitors. Again, we'll talk a little bit more later on about the exact implications of that and exactly how you deal with it. But just keep in mind that you can't necessarily always throw those AC coupling caps in. Okay. Okay. So now we can actually sort of start talking a little bit more about the details of the transmitter. And this one will actually be sort of a little bit quick because I think we've kind of talked about it already. So the other terminology that you'll hear, which is, again, unfortunately often intertwined with voltage mode versus current mode, is that if I am going to be using some sort of passive element, meaning, for example, resistors, to set the value of my termination, then there's kind of two ways I can do it. The first way is I can put that termination resistor in series with the rest of my stuff. Okay? The other way is I can basically put that termination in parallel with the rest of my circuitry. Okay? So again, obviously the way I've drawn it here, in this particular case, the series version I've used for a voltage mode driver, and the parallel version I've used for a current mode driver. Okay? So now, what do you guys think is kind of the trade-off between these two? What's good about each one of them? Or alternatively, what's bad about each one of them? Maybe I'll ask it more specifically. If you really wanted to get, a very, very precisely controlled impedance, and let's assume that magically I gave you perfect resistors, so don't worry about that for a second. Which one of these two would you choose? Which one do you think gives you a more precise one? I saw one vote at least. So who votes for series as being more precise? One brave soul. Okay, that's good. Who votes for parallel as being more precise? Okay, well, so great. It is indeed parallel. Now, why? So why is parallel more precise than series? Yeah?
They are like shunt parasitic capacitances, which will change the...
Oh, okay. So it is sort of related to that, but even, let's say, from a DC standpoint.
Well, in the series, you kind of still have the devices in the path. But in the parallel, you're seeing the high output impedance. So.
Right. So that's basically what it comes down to is here, if you want to make it really precisely RT, then you need essentially the resistance of the transistors to be equal to 0. Okay? Here, if you want to be precise, then that just means that, the RO of your device, okay, well, I'm going to put a roughly here. You want it to be infinity. Of course, you can't get infinity, but the good news is, of course, the way the devices work, if you keep things in SAT, then indeed you can get pretty high output impedances. And certainly from a power standpoint, it's a lot easier to get high output impedance with low power than it is to get very, very low output impedance with low power. Okay? So typically, indeed, that parallel one is better. Yeah?
I think that's arguable, right? In this day, like the newer technology are always not that high. It's like only...
but so still, if I wanted to make my... is GMRO greater than 1 or not?
It only, it's not very high though.
Yeah, even if it's 4 or 5. So by the way, you are actually getting into something which I will touch upon in 1 second. Okay, but you are right. It's not that getting output impedance is free, but remember, increasing output impedance, at least fundamentally, doesn't have to cost you power, right? Getting really low output impedance pretty much always means somehow you paid for it. Okay, because something somewhere needed to actually, sustain a lot of current with a very small voltage. Okay? So in the example of, let's say indeed, like you were complaining, let's say you have really crappy technology, which, with GMRO of only 3 or something like that. And that just wasn't good enough. Well, what do you do?
Cascode.
Yeah, you cascode, or you make a slightly longer channel, or one of these other kinds of things, right? Now, so that's absolutely correct, but now what's the bad news about doing the parallel version? And this will maybe be a good, let's say, prefetch for what we'll talk about next time. So what's the bad news about the parallel version?
Swing, right?
Yeah, exactly, right? So just like in 240, your quote-unquote swing is going to be reduced. Okay? In other words, you always have to support that VDSAT across the device there, right? As an example, if I looked at what was like the lowest supply I could have used in this driver versus that driver, at least ideally speaking, I could have actually used a lower supply with that voltage mode driver than I could have with the current mode driver. Simply because I wouldn't have to support that extra VDSAT for the current mode driver to get it to work. Okay? So we'll see again in a little bit later on, this actually has some pretty, let's say, interesting implications on the way we're going to want to build these drivers. So I think we're almost or basically out of time for today. What I'll start doing next time is, I'll just briefly tell you a little bit about what are some of the different standards of transmitters and receivers that you might be working with. As I've said here, they're all sort of working on the same basic principle. So what I'll do is we'll start actually diving some more really into some of these trade-offs that I've been hinting at about power consumption versus swing and how you really build those drivers and sort of what the considerations there are. So with that, again, no lecture on Thursday, so I'll see you guys all hopefully on the following Monday. So see you there.